there are sort of two branches portrayed in this diagram. One is the sort of basic research branch. Why do we study the sun? Well, to understand how stars work, how heating works, the nuclear furnace inside this object is fascinating. Also how the plasmas, the charged particles, gases flowing from the star really affect the environments of the planets, such as the Earth, other planets, and extending this to the plasma universe. The other branch of this is really the more applied side. I'm going to emphasize that tonight. That's the study of how the space environment, changing space environment, can affect many, many different aspects of what we pursue as humans. Humans in space, spacecraft operations, power, communication, even the possibility of effects on the Earth's climate. When we talk about space weather, it's not too much of a leap to start talking about regular weather. And when we do that, there are many wags who have commented on this. Oscar Wilde, for example, said, "Conversation about the weather is the last refuge of the unimaginative." That's probably sort of true. On the other hand, American humorist Ken Hubbard said, "Don't knock the weather. 9 tenths of people couldn't start a conversation if it didn't change once in a while," and that's probably also true. So somewhere in here, space weather as sort of the same kind of a deal, but sort of an operational definition of what space weather is described here. It's the changing conditions on the sun throughout space and in Earth's vicinity that can affect the performance, reliability of space-based systems, ground-based technological systems. It can certainly endanger in ways we'll talk about human life and health, and it can affect a whole range of different kinds of technology that we've surrounded ourselves with. If you think about 150 years ago or so, there were virtually no technologies, only the telegraph, which was the internet of its age, might have been affected by the space environment, and that was only sort of peripherally, whereas today we have all kinds of systems that are affected. So the main driver for space weather, changing space weather, is the sun. If you have X-ray eyes, with seen soft X-rays when you were out in space, as the Yoko, the joint Japanese-U.S. satellite, was over about a 12-year operational lifetime. And you looked at the sun in these snapshots over an 11-year sunspot cycle, you'd see the sun was very active with bright active knots of energy conversion, magnetic energy being converted into X-rays and hot plasmas. And then as time progresses, the sun becomes very quiet, very passive, and then it grows and waxes and wanes over this kind of approximately 11-year period. But it's highly variable, and we'll talk about this variability in a second. Now, I was going to turn up the sound here a little bit, if I can. You still probably won't be able to hear this terribly well, but I want to. I can hook that in. Let's see. The sound's not that crucial. Never mind. Okay, if you look at our sun in ultraviolet and other wavelengths, as the Solar Dynamics Observatory is doing now, and this is not an artist's concept or an animation, this is real data, and what you see is this boiling surface on the sun. You see magnetic concentrations called sunspots. You see the merger and the collapse of these. You see the structure, the upwelling and downwelling of gases in the sun's surface. You see large regions, intense regions of emerging magnetic flux. And you also can see spread over the surface of the sun these regions of magnetic loops that are constantly changing and constantly evolving and are expelling huge blobs of material at immensely high speed. These prominence materials can be go up to millions of degrees above the 6,000 or so Kelvin surface of the sun. Here you see the black and white showing the polarity of the magnetic field. But this kind of material emerging from the sun and these kinds of disturbances, blasts of large material magnetic loops moving out from the sun toward the Earth are the principal drivers we think about for the space weather effects. Now, interestingly enough, this first year of Solar Dynamics Observatory was sort of the quietest that the sun has been. So everything you saw there was really during the time when the sun was at its quietest for probably 2 centuries. And in a piece a couple of years ago, we talked about this. The sun has been very, very quiet, extraordinarily quiet in this period 2008 to 2009. And we really don't understand fully why. But Ron Turner, a colleague, published a very brief paper looking back at the 400-year sunspot cycle. You may recall that sort of systematic observations of the sun were undertaken by Galileo about 400 years ago. Almost immediately after we started looking closely at the sun, I guess the sun got shy or something, went into a period of extreme quiet called the Maunder minimum. This more systematic counting of sunspots began again in about 1750, and again there was a very low activity period. This is sunspot number versus time, and there was a period called the Dalton minimum. Anyway, Turner looked at this recent solar minimum time, plotted it in from 2 years before minimum to 2 years after, and what you see is that this recent period of inactivity is in many ways comparable to what went on about 2 centuries ago. So this recent solar activity or inactivity is really quite striking. But just a few years before this, in 2003, the sun was extraordinarily active. Again, this is in extreme ultraviolet. These are real data. And what you see is a sort of telescoping back from the sun. This is an X-ray flare. You see the snow that then appears in the picture. You see the flare here again. The snow that is very energetic particles from the sun that are sort of blinding the CCD cameras. And here you see occulting disks that are blocking the visible disk of the sun. And the blast of material that you see, this envelope of halo of bright gas, is really the coronal mass ejection, what we call coronal mass ejections. These are the principal drivers we worry about for causing space weather in the Earth's vicinity. So this is now more of an artist's concept in animation showing this. This again is the sun. Something on the sun leads to a loss of stability. A large blast of material can emerge at very high speed. I'll talk more about this in a while, but this can be of order 10 to the 16th grams. That is 10 billion tons of material moving out perhaps at several million miles an hour, can collide with the Earth's magnetic field. If the magnetic field orientation is proper, it can sort of open the gate and allow huge amounts of energy from the flowing solar wind to enter into the Earth's magnetosphere, can lead to auroral brightenings, and can cause powerful currents in the Earth's upper atmosphere. And so these are the kinds of events that we think about as being principal drivers. So if we again think about the period in November and October, November of 2003, what I was calling the Halloween storms, there was not really one of these blasts of material, but a huge number of them. They've spread out and filled sort of the entire inner heliosphere. It took several months to get out to the edge of the solar system, but eventually the Voyager 1 and 2 spacecraft saw these blasts of material. So it's not just that the Earth is being picked on, but all the planets in the inner part of the solar system, including Mars, Jupiter, all of these planets can be subjected to these powerful solar disturbances. Scientifically interesting, but also space weather concern. So to motivate things a little bit here, probably most of you know about geostationary orbit, the place where we have weather satellites, communication satellites, all kinds of sort of operational civilian spacecraft and military spacecraft. This is a map of a somewhat outdated one now, probably from 10 years ago or so, but just showing that it's sort of every available slot is filled around the geostationary orbit with spacecraft that are trying to make useful measurements for societal needs. It's estimated to be several $100 billion worth of assets in this region of space, and all of those can be sort of blasted by space weather events, and there can be significant consequences for them. So when you think about the space environment, there are many different ways that space charged particles from the sun or the radiation environment around the Earth can affect satellites. So this is sort of an idealized picture showing that there can be effects due to high-energy ions, so-called single-event upsets in sensitive electronics. There can also be deep dielectric charging. I'll talk more about that in a second, and even surface charging. So all these spacecraft operating in the near-Earth region can be subjected to tremendous space weather effects. Let's just talk about this for a second. As you can see, I hope from a little schematic diagram here, charged particles can go through, deposit a lot of energy in the electronics, and can cause bit flips and effects like that. Maybe a more visible effect is to just see the blinding of CCD cameras that can occur associated with this. This is during the sunspot maximum of about a decade ago, a little over a decade ago, and this is again is an extreme ultraviolet telescope image, beautiful image, I think, of the sun right at the sunspot maximum. And just about 6.5 hours later, this same camera system is now virtually blinded. This is all due to hydrogen particles going through the camera and essentially blinding the camera system. So it doesn't take a lot of imagination to think about human eyes or human brains out in space being subjected to this kind of hundreds of million electron volt charged particles passing through and dumping lots of energy. So the solar particles are one big worry, and probably one of the limiting things for human exploration beyond low Earth orbit. Now if the last decade was the decade of solar observations, we've now gone, in a sense, to the other end of the system, to the earthward end. And so I'm delighted to be the principal investigator of two instruments that are on board, what are called the Radiation Belt Storm Probes missions, or the Van Allen probe missions, as they've been renamed. And on the 30th of August, with a beautiful launch of an Atlas V rocket from Cape Canaveral, we have the spacecraft being launched into into an elliptic plane or near Earth elliptical orbit. And so here are the spacecraft. This is artist concept, not a photo. And the spacecraft are put into what's essentially a geostationary transfer orbit, moving through the Earth's magnetic field and also mapping now the radiation region around the Earth and trying to map this inner and outer Van Allen radiation belt zone. And this is one of the principal kinds of effects we worry about for near-Earth space, is the effect of these very high-energy particles trapped in the Earth's magnetic field that can cause significant operational problems and upsets. So that's more related to this phenomenon, which is that high-energy electrons in the radiation belts close to the Earth here can penetrate through very substantial amounts of shielding through the spacecraft walls, through the box walls, and can penetrate into insulator material, bury themselves in insulator, and can build up enough to cause an electrostatic discharge. Some of you may know about that if you're involved in electronics or so, how damaging these electrostatic discharges can be. In effect, they are really like small lightning discharges within the confines of the electronic systems, and that can really cause very substantial damage if it occurs in the wrong place. This is from JPL, just showing how electrostatic discharge on a trace really caused a major disruption. This can lead to complete failure of satellite subsystems or systems. We've seen many cases where this kind of thing has occurred. For example, this is from a case that we studied quite intensively about a decade and a half ago. It was really three nearly identically designed spacecraft called the ANIC satellites. These are Canadian communication satellites. And they were providing phone service, television service, radio, newspaper kind of linkage from the east to the west coast of Canada. And they were subjected to these very high energy electrons in the radiation belt. And in rapid succession, all three of those failed, or at least stopped working temporarily. One of them was out of commission for over 8 months. It cost about $70 million to recover, and ultimately sort of limped through until the spacecraft could be replaced. And so this is just one of many examples where the space environment has clearly been implicated in causing satellite failures. So today, or nearly today, I guess, 2012 to 2020, it's been argued by our friends at NOAA and other places that worry about space weather that there are many new drivers coming online that are where we have concerns about the effects of the space environment on our modern technological systems. The global positioning system or global navigation systems, not only in the United States, but in Europe, in Russia, and soon to be in China. The next generation air transportation system, concerned about space weather, we'll talk about. A big one is the increased vulnerability of the power grid, continental scale power grid, commercial satellites, exploration missions to the moon and beyond. The United States is lagging a bit there, but we hope that will be resurgent. The commercial space enterprise, that is humans going into space, Arctic economic development, a whole bunch of other things we can talk about. So let's talk about the global positioning system, GPS. How many of you use or have ever used GPS for any purpose? I don't. Anyone have not? Know about GPS? Yeah. So it started, about GPS was first introduced in the 80s. I was actually at Los Alamos at the time, and I thought, well, this is interesting. It was for military purposes then. Famous or infamous President Reagan decided that it should be used for and made available for civilian use as well. And over time, the sort of commercial use of GPS has grown dramatically and is expected to reach something of order $500 billion to $1 trillion kind of business space, but it's now being used for all kinds of things. And you all have probably used it for many purposes, but not just for the positioning, but for surveying, for construction, seismic data collection, oceanography, management, data management, just an unimaginable number of things, and it's just become so ingrained in our daily lives, it's really quite striking. And yet the GPS systems are really subject to several different kinds of dangers associated with space weather. I'll talk more about the effects on the spacecraft themselves, but intense activity from the sun can lead to what are called scintillations in the Earth's ionosphere. That can lead to problems with transmission of signals from spacecraft to the ground, can lead to ranging errors. And the airlines have wanted to use GPS in order to fly planes closer together, both vertically and horizontally. And they really are subject to these kinds of effects. So adverse space weather can cause significant problems, can cause amplitude fading, range delays, scintillations, and so forth. One of the hot ideas that the FAA had, US had, was to use the wide area augmentation system. So to back up the ground transmitters that gave reference locations, the idea was to use the GPS signals in order to be able to, as I say, fly planes more efficiently. And this wide area augmentation system was being evaluated during the October 2003 storm that I talked about. In this diagram with this animation, blue is good, red is bad. And so what's being indicated here is the total electron content. And by the time we got into this storm period a bit, the whole of North America was basically made unusable for couldn't, and this lasted for about 30 hours or so. And so they had to really go back to the drawing board and look more carefully at the implications for the systems as they were then designed. Now more effort's going into trying to make the GPS immune to these kind of total electron contact problems, but right now doesn't look so good. Another way the airlines are affected is just by flares like this that cause intense emissions. The entire sunward side of the Earth, the entire day side, can have a loss of high frequency radio communication. And you may or may not know, but we still rely very heavily on HF communication for air, for civilian and the military air traffic control and communication. And so this is another major concern for the airlines. Now one of my favorites, since I fly a lot and like to get from one place to the other as quickly as possible, is a major change over the last decade has been from going long sort of multi-stop routes at mid-latitude is to flying over the poles of the Earth. And so United Airlines, many of the other long-haul airlines are now flying from North America, Chicago, Washington, over the polar regions to Asia. And there's just been an exponential increase in the number of flights that are occurring following these kinds of routes. Now the requirement is that these aircraft have to remain in constant radio contact with the company, with ground facilities, and when you get above 82 degrees latitude, they can no longer use satellite communication for this purpose, and so they have to rely on the high frequency, very high frequency radio communication. And when there is a powerful solar storm, as let's go back to our favorite event here in October 2003, I don't know if you can see this very well from where you're sitting, but this is a polar view, and this red region is where there were huge fluxes of solar energetic particles funneling down along the magnetic field of the Earth right into the polar region, and really causing radio blackout over this very broad sector. So when that happens, airlines have to stop flying the polar route. They have to fly alternate routes. That's longer and costly, and sometimes they cancel flights. And so there have been many instances where in recent solar activity times where the airlines have had to cancel flights because of this. So this litany, I'm giving you a litany of different kinds of space weather effects. Another one is the human space flight. We, of course, have been changing the way we're doing human space flight. We're relying more on the Russians to get us into space and so forth. But the International Space Station is operating. Extravehicular activity is an important component of this quite often. And when the space radiation is enhanced, the EVAs have to be curtailed or eliminated. Again, this is a major space weather concern. I was privileged, I guess about 6-7 years ago, to chair for the National Academy of Sciences and Engineering a study looking at space radiation hazards and space exploration, human space exploration. And we did a report talking about the challenges that are faced by humans getting into space, and especially being outside the protective envelope of the Earth's magnetic field and atmosphere. This is one of the tables from that report. Many of you may be quite expert about biological effects, I don't know, but the radiation risks can include cancer, degenerative tissue effects, damage to the central nervous system. Acute risks, death is a bad one of those, but vomiting in a spacesuit makes for a very unpleasant time and can be life-threatening in its own. But just looking at this range of different consequences and realizing that if we're going to go to Mars, it's going to be months, many months of travel time outside the Earth's protective umbrella. The probability is very high that there will be solar particle events that could be life-threatening, probably would be, and the return. Once one gets to Mars, the atmosphere there can be somewhat protective, but nonetheless, this is still one of the tall poles for human space exploration, is the effects of the space environment. So we've gone through this litany of and maybe a mind-boggling kind of range of different effects of space weather on our technological systems. But I think it was about 5 years ago or so, we started to ask the question, what does it really cost our society for space weather? What are the real economic consequences? And while there have been many studies of floods and hurricanes and all these kinds of natural calamities, earthquakes, there really hasn't been a very systematic look at the effects of space weather. So we wanted to ask, what are the consequences? How likely are these? Are there things that can be done that could mitigate the effects? And so I was privileged to chair a committee, again, for the National Academies. And we've had not only advocates, cheerleaders for space weather like myself, but also people, specialists in spacecraft design like Mike Boudreau from Northrop Grumman, people from United Airlines interested in these effects on long-haul airline flights, people, real economists like Kevin Forbes, people from the power grid and so forth, and another economist, Art Small. And so this group was really charged to put together a workshop to ask these questions and then to call in experts from the various kinds of industries and government agencies to really try to start to answer the question about effects on the global positioning system. What does it cost? Power industry, what does it cost? Aviation, what does it cost? And so these econometric analyses were geared eventually to trying to improve and understand the value of forecasting severe space weather events. This is the cover from the report. It was published at the end of 2008. It's been one of the, I'm told, one of the most popular recent reports from the National Research Council. It's been translated into several languages. The most recent copy I have on my desk is translated into Chinese, and I can't read it, but I believe they've probably done a good job of translating what we had to say in this report. So the anticipated benefits, I think they've been borne out then, is that at least we've begun the process of looking at these economic analyses, impact analyses. We're providing, through these kinds of efforts, better guidance for policymakers, better rationale for agency budgeting, better understanding of the high payoff forecast, and clearer guidance, say, for human exploration, and maybe improving societal appreciation for space weather risks. And at least in part tonight, I'm trying to continue that by advising all of you about some of these risks. Just some of the, again, the highlights, and I sort of touched on some of these, I guess, but all of these adverse effects that I've mentioned to you are delineated in this report. One example was a rather unexpected powerful storm that occurred in January 2005, for example. 26 United Airline flights were diverted in association with that one storm. The 2003 storms I've talked about, the wide area augmentation system, the outage of Canadian satellites, all the things that I've sort of listed and many more are cited in that report just to illustrate the effects. This is a figure from the NRC report that I was mentioning to you. And just one thing you might be interested in. This blue or purple curve is really the number of reports of significant operational anomalies, like failures and anomalies are documented in Mike Boudreau. I mentioned him from Northrop Grumman. He put together his own kind of database of significant operational effects. You can see these sort of go along and are up and down year to year. But just in this 1 year, 2003, associated with this Halloween storm, like a doubling of the number of severe operational anomalies just in his database associated with one powerful solar storm. So one event can make a big difference, quite honestly. Perhaps the headline story from our economic and societal impacts report was an increased appreciation of the effect of space I believe it came from Homeland Security, but it tries to illustrate the interconnectedness, the interdependencies of society. Just consider what you might call the cornerstone technology of our age, which is the electric power grid. And the arrows are meant to try to indicate some of the interrelationships that exist. But without electric power, you quickly are unable to pump fuel, have oil and gas. You can quickly lose communication. You can quickly lose the ability to pump water and have potable water for societal needs. You can have disruptions of banking and finance. Transportation is rapidly disrupted, emergency services, government services. And so without electricity, as was seen recently in Superstorm Sandy, without electricity, society pretty quickly starts to melt down. Now, the electric power grid has been around and with us on continental scale for a century or so. It's operating very near its operational limits, quite honestly. And the grid is becoming increasingly vulnerable, as many experts have said, to the effects of severe space weather. And space weather can cause transformer winding failures. This is on a sort of a small scale. The most severe risk that's faced by the electric power grid is really now the extremely high voltage backbone, power grid backbone. This is really where we're operating at hundreds of thousands of volt kind of potential differences. And this is again from the NRC report that I was telling you about, the severe electrojet, that is currents flowing in the Earth's upper ionosphere coupling into the power grid. And purple here sort of delineates the major backbones, of black, I guess, delineate the backbone elements of the power grid. And one powerful solar storm that was modeled in some detail by our colleague John Kapman suggests that there can be very severe effects over like a third, the eastern third of the United States is very susceptible to these kind of failures. What essentially happens is that these house size, extremely high voltage transformers melt down, and when they do, they have to be replaced. There's not you can't go to the store, you can't go to down the street to one of the electronic stores and buy these. You have to build them specially. And so well over 100 million people could be affected for periods of weeks, months, or even years. And so the collateral damage here of power grid failure, all the things that I talked to you about, could be hugely severe. Now, how extreme can space weather events get? About 150 years ago, there was a very powerful event called the Carrington event. In fact, this was the first white light flare that was ever observed by scientists using telescopic means. Richard Carrington was a solar astronomer. He was mapping sunspot groups on the sun. He noticed a very bright white light flare, first time this has really been seen. He ran to get a colleague. They came back and looked at this, and some other observers had seen the same thing. This occurred in late August of 1859, and by the time they got back and could really look at this, it was already fading. But shortly thereafter, there was a huge geomagnetic storm, a storm in the magnetic field surrounding the Earth. And there were actually two of these sort of powerful events back to back. During this event, the auroras were seen down to essentially the magnetic equator, down to Cuba and low latitude regions around the Earth. There was such powerful aurora occurring in, say, northeastern United States that people could read newspaper by the aurora light. There were powerful currents induced in the telegraph lines. They could disconnect the batteries and still be sending telegraph signals because the currents that were flowing in the telegraph wires were so strong. Sparking was occurring in telegraph stations. There were fires that broke out as a result of that sparking. There were a lot of deaths that were associated with the fires that broke out because of that kind of sparking. So as I mentioned before, this was the internet of that age. It was severely disrupted. If you want to, we did a little article in Sky and Telescope in February of 2011. If you'd like to read about that, it's kind of interesting to just read some of the stunning observations that people made about the change in the environment and the aurora and so forth. But anyway, this extreme event in 1859 still is sort of the record holder. But an event like that occurring today, not when we have one technology, but we have multiple technologies, especially the power grid, the estimate is that this could take multiple years to fully recover for the reasons I was telling you about. Could lead to economic losses of trillions of dollars. This used to be a big number before the fiscal cliff, you know, and all that stuff. $1 trillion when we wrote the report meant a lot. Now, you know, it's just not so important, I suppose. No, I mean, really, this would be a severe effect for society. Now you might say, well, 150 years ago, that's pretty old and moldy, and what's the probability of this really occurring? And we're sort of in a quiet solar period now, so maybe it's not so much to worry about. This 1859 storm occurred in a weaker than normal, average kind of sunspot interval. In fact, it was quite a bit below the average over historical times. Another storm, the one that Kaplan used to estimate the 130 million people being without power, also occurred during a pretty weak sunspot activity period. And of course, now we are in a relatively weak solar activity period, many people say. I go back to the period in 2003. We dodged a bullet, in my opinion. Despite how powerful the storms were that we saw that actually hit the Earth, just a few days later, on November 4th, let's say 5 or 6 days after the events that affected the Earth, there was the largest solar flare that ever was recorded. It occurred when the active region had moved to the limb of the sun, so it was just around the corner around the sun, you might say. This was the largest flare that we typically keep track of is a so-called X10 flare. The largest flare that had been recorded was in that neighborhood before. This was estimated to be an X28, so that's 2.8 orders of magnitude higher in intensity. The coronal mass ejection that blasted off associated with this was moving over 3,000 kilometers a second, so about 6 times faster than what we usually worry about for solar wind speeds. But it's actually more interesting than that, because just about, just at the end of end of July of this past year, July 2012, the spacecraft Stereo A, operating out in space, saw just a spectacular solar event. So again, this is the nested kind of picture. So here's the active sun. You can hardly see that. You see this chronograph, and you see this huge blast of material coming out, and it's almost a perfect halo. So it's coming right at the Stereo A spacecraft. So Stereo A is at about 1 AU, about the distance of the Earth from the sun. And this coronal mass ejection that was seen to lift off was moving 3,500 kilometers a second, faster than what we saw in 2003. It was a very nasty active region on the sun, and this blast of material came out. Now, we're looking down on the top, so this is the solar system kind of weather map, okay? We're looking down on top of the sun here in the center. Stereo A is over here all alone. All the rest of the things we're interested in, the Earth, Mercury, Venus, Mars, everything's nicely out of the way. So this was a natural experiment. The sun chose to perform an experiment for us to tell us how bad it can get. And this is really, the colors here are really mapping the solar wind speed. So this thing was coming out at 3,500 kilometers a second or so. It actually went from the sun to the stereo position in 17 hours, faster than the Carrington event. So if this had hit the Earth, I think we'd be having a very different conversation today. We've actually taken this and modeled it. We've looked at the magnetic field measured by the stereo spacecraft. We've estimated the solar wind speed profile, modeled that. And actually this leads to or would have led to a geomagnetic storm at Earth that's larger than anything that was seen in the 20th century. So we would have had something in the league of the Carrington event in July 2012 if this had occurred just 7 or 8 days earlier than it did occur. So I don't think we have to look back 150 years to say, are there severe space weather events? It's just a question of whether we get hit by the bullet or not. So new drivers, the next generation air transportation system, it's going to be GPS based. I've warned you about the possible consequences there, and this is being taken seriously, being built into the NextGen estimation. It's not just the United States. Space weather is something that doesn't really respect geographic or political boundaries. It's really something that affects all developed and developing countries. And just the range of concerned users is really quite stunning. If you go back to the 1940s, about the only thing that military planners say are really worried about was shortwave radio propagation. Then radar came to the fore. But as we've gone along here, we've gone to modern times, more and more technologies have come online that worry about the effects of the space environment. And almost all of these, very few of them really fall off the screen, so to speak. Almost all of them remain of concern. But now we have commercial TV, of course, GPS we've talked about, satellite operations, atomic clocks. Our friends at NIST can see the effects of geomagnetic storms. Precision-guided munitions may not be your favorite thing, but there you go. Airline polar flights and so on. So there's just a boatload of different industries that are concerned, should be concerned. And I'm sort of coming to the end of my remarks here, but let me just say that we've had a wonderful period of observing the sun, the driver for the system. But now new missions like the Radiation Belt Storm probes join quite a constellation of scientific satellites operating in the near-Earth region that are providing an observatory fleet for studying the connected Sun-Earth system. And I think it's wonderful, but it's also worrisome. We should, if we're going to do space weather right, we can't just rely on the scientific satellites. We also have to really have 24/7 continual operation of space weather monitoring systems. And I believe that this is one of the key things we really need to address as a society is what are we going to do to assure that we continue to observe the sun and the consequences near Earth. So let me wrap up by saying that space weather, the effects of the sun, are really things that we have to address. We have to understand what it is that leads to these coronal mass ejections. We have to understand what's likely to hit the Earth, what is not likely to hit the Earth. We have to be able to realize that the consequences of these powerful coronal mass ejections can be the kind of power blackouts that I've talked to you about. We've also gotten a magnificent understanding now that these nice cartoon, smooth, laminar kind of pictures of the Earth's magnetic environment, the Heliosphere, really are not accurate at all. That it's a much more dynamic and fluctuating system. These powerful currents flowing in the Earth's ionosphere can couple into the pipelines, into the power grid in ways I've talked to you about, can lead to substantial failures of the sort that we've seen historically, and perhaps worse than anything we've seen historically. And the effects can be seen both in the ground-to-ground communication because of effects on the ionosphere, as well as the, and consequently in aircraft, or it can be from space to ground and can cause, therefore, upsets. And many of the things we rely on, the kind of electric coupling that we rely on for our ATMs, for GPS, for precision agriculture, for navigation at sea. And the effects can be both directly in the spacecraft as well as in the entire constellation of spacecraft and disruptions that may be associated with GPS or geostationary birds. And so ultimately the effects on humans and the space station or as we move beyond. And so we've got a lot of these scientific assets, but we now need to start to selectively augment these with operational satellites. So I think that in many ways understanding the connected Sun-Earth system is like solving or putting together a jigsaw puzzle. We've got a lot of models, we need better observations, and by combining our scientific and operational systems and models, I think we can solve this space weather puzzle. So let me wrap up and I'll take a few questions. I think the challenges of space weather affect all developed countries and both civilian and military systems in ways we've talked about. I often remark that I think this understanding of space weather is really basic research with a high public purpose. And future space exploration and most human endeavors in one way or another, I think, will require that we have major advances in physical understanding, and we have to improve our transition of that understanding from research to operations. And finally, one of the challenges in some of the things I do, and maybe I should have acknowledged this from the beginning, is I think there are very real threats, but we also have to say, how can we do this? How can we talk about these kinds of things without being unduly sensationalist and sort of avoid the Chicken Little syndrome that the sky is falling? In some ways the sky is falling, but I don't want to be too alarmist about that. So I'd be happy to talk about that philosophical point. Thank you very much.